Well, hello there guys, Mr. G here, and we are going to be making another video today on revision about conservation of momentum. So we are going to also be doing two questions. This first question is was question 2 from June 2021 at the Northern Cape province. It's a good question. I previously did a video but the quality was not good, so I'm going to redo it. This question said block A of mass 0.20 kg moving east at the speed of 20 meters per second collides with another block B of mass 0.30 kilograms moving east at the speed of 5 meters per second. After the collision, block A moved east at the speed of 2.5 meters per second as shown in the diagram below. Ignore the effect of friction, and that is the first thing to have in mind. The system is closed. System is closed because there is no external forces acting. Now the picture is here. We're having a before collision where block A is moving to the east. Remember, they were talking about east and west. So east is not the same as right. Now it is moving east and it will collide with block B. Now, as we always do, let's quickly write the data here. So we have the data, we can move on to the question itself. The first question, 2.1, says state the law of conservation of linear momentum. So the first question 1.1 says state the law of conservation of linear momentum in word. 1.2 say calculate the velocity of the block B after the collision, and 1.2.2 the magnitude of the impulse on block A. So let's start with question 1.1. And these laws state that in a closed or isolated system, that is very important, total momentum or total linear momentum is constant. Now here, note that you cannot mess either closed or isolated system, and the word total is also very important, okay? So please don't forget that. Now let's go to the calculation. Calculate the velocity of the block after the collision. For this one, we have to use the law of conservation of a linear momentum and not something. If in the previous question they ask you for a law, it's a high probability that the upcoming question is to apply that law. So let's write down the law, but we did before many times, so I'm going to fast forward a little bit for question 1.2.1. And so here is the answer. Now the important thing I didn't mention before, I didn't do it because everything is moving to the east. So obvious east is going to be a positive, but that is not very important here because everything is moving in one direction. However, it's part of the question, you must do it. So let's go into question 1.2.2, and this one say calculate the magnitude of the impulse of block A during the collision. So you have to use now the impulse momentum theorem. So for question 1.2.2, let's use the impulse momentum theory, but this one I'm not going to fast forward because we did not practice too much. So impulse is equal to change in momentum. This is the impulse momentum theorem. Now we're working with block A. Impulse A is equal to change in momentum of block A, and change in momentum will be equal to mass A multiplied by the final velocity A minus mass A multiplied by the initial velocity A. Now the mass is constant, it do not change. If you want, you can use a common factor, otherwise you may substitute here. I'm going to use a common factor because it's more mathematics. So here is final velocity A minus initial velocity A, and the answer will be the following. The substitution first is 0.2 open bracket 2.5 is the final velocity of block A minus 10 is the initial velocity of block A. And when you solve this one, the answer is going to be negative 1.5 newtons second. Now, what does negative 1,5 mean? It means it's in the opposite direction and everything was moving to the east. We put here is positive, so we are going to write the final answer. Impulse of block A will be equal to 1,5 newtons second west. That is the final answer for this question. I hope you understand. This is a quite easy question. We'll go on to another question. Okay, so the second question we are going to be doing is a question 5, or it was question 5 from September 2017 at the Eastern Cape province. This question said a 5-gram steel marble cannon is fired horizontally to the east from a 2-kilogram model cannon that is stationary on a flat frictionless horizontal surface. You can see here is a flat frictionless horizontal surface, means the system is going to be closed, and the system for us is going to be the cannon and the ball, the marble. Okay, this thing here, later on we're going to be talking about that one because things change a little bit. The cannon is placed 0.32 meters from a fixed barrier, as you can see there. Okay, now at the instant the steel marbles leave the cannon start moving backward at constant velocity. So let's write some data here on the picture. First of all, the initial velocity of this cannon is 0, as well as the initial velocity of the marble. I'm going to write the marble like this, and cannon with a letter C is equal to 0. The marbles move forward with a velocity we're going to find out later is moving them. This is after firing the marble, and the cannon is going to move backward, okay, as a result of that firing. Now, the cannon is going to move backward at constant velocity. So, once start moving, it's fine, start moving with certain velocity, but after that it's going to move with constant velocity. So, the cannon, let's say from here to there, the velocity was constant. At the beginning it was 0, but then when it started moving, stayed moving with that velocity. And then the first question, 2.1, says state the principle of conservation of linear momentum. Where we did it in question 1.1, so we're not going to redo it. We just want to write the answer straight as this. Now, question 2.2, after firing the cannon, take 0.33 seconds to collide with the barrier at the distance of 0.32. So from here, where the cannon is, to there, the time it took the cannon was 0.33 seconds to arrive in there. Remember, that is after the collision. Before the collision, the cannon is not moving. After the collision, the cannon was moving with constant velocity for a while. Okay, now we carry on reading. Calculate the speed at which the cannon collides with the barrier, and calculate the speed at which the steel marble is firing from the cannon. 2.3, the cannon bounces back from a barrier at the speed of 0.4 meters per second. Calculate the magnitude of the impulse by the barrier on the cannon. So let's start answering 2.1. We did it already, so we're just going to copy the answer there. So it is the law of conservation of linear momentum. Note that in the previous one they say law, and in this case they say principle. It's the same thing, okay? We're not going to be discussing that. Now, after firing the cannon, take 0.33. Let's calculate the speed at which the cannon collides with the barrier. This is question 2.2.1. Okay, now what we have, let's write quickly the data here. And that is the data. So what formula we can use? If the motion is constant, we can say that the velocity is equal to the displacement divided by the time, and that's it. This is equal to 0.32 divided by 0.33, and the answer is going to be 0.97 meters per second. They want us to calculate speed, and speed is a scalar quantity, so we don't have to give direction. So the answer for this question is that one there. However, if any of you want to use another formula, for instance, you can say that the displacement is equal to initial velocity multiplied by the time plus half acceleration multiplied by the time to the power 2. Here, all this one here is going to be 0, because if it's moving at constant velocity, then the acceleration is 0 and you will get exactly the same answer as it is there. It's no different, so we're not going to waste time doing that one again. So let's go to question 2.2. Now, in question 2.2.2, they say calculate the speed at which the steel marble is fired from the cannon. So here we are going to use the law of conservation of linear momentum 2.2.2, and because it's exactly the same as before, I'm just going to fast forward this part. So that is the data. Let's now use the law. Now, before we substitute the masses, note that this one is given in grams, so we have to convert. Okay, so this one is going to be 5 times 10 to the minus 3 kilograms, and that is what we are going to substitute. Now, note the following: this one, the initial velocity is 0, so it's going to be 0. It's not a need for us to substitute everything. So what do we have now? And that is the answer. You don't have to write direction because they're asking you for the speed, and speed is a scalar quantity. So now we can go to the last equation, which is 2.3. 2.3 says the cannon bounces back from a barrier at the speed of 0.4 meters per second. Calculate the magnitude of the impulse by the barrier on the cannon. So we did previously a question almost like that, so it's going to be quite fast. It's question 2.3. You are looking for impulse, and then what we have is the impulse on the cannon, and this is equal to the change in momentum on the cannon. So if we carry on, now note the following here. The final velocity of the cannon is the bouncing or rebouncing velocity of that cannon. That is very important to notice. And the initial speed is not 0, it's the velocity with which the cannon is going to hit the barrier, okay? Which is obvious not 0. So it's not very difficult. The mass of the cannon is 2. The final velocity of the cannon is the one which it moves backward, which is to the east, and is 0.4. Is given to us, minus the initial, which is west, and is minus 0.97. Remember, we said for this question, we said that the east is going to be positive. So for this one, we're going to do the same. And the final answer, after you do this, is going to be equal to 2.74 Newton second to the east. But I think they're asking you for the magnitude. Let's just make sure they're asking you for the magnitude, so not direction. And this is the final answer. These are questions from question papers. I hope you understand. Thank you for watching. Thumb up, subscribe for the channel. Next time we go to the last part of this topic, which is collision. Thank you for watching. See you, Mr. G here.